Hello, welcome back. Today we're going to be applying Hamilton circuits to approximate solutions to the traveling salesman problem. Now, first our notation that we're going to have, our definitions. First item we're going to have is called a complete graph. So a complete graph is one that has exactly one edge between every pair of vertices. So we have a way of going from every vertex to every other vertex. Each vertex is connected to all others. So in this example, vertex A is connected to C, B, and D. Vertex C is connected to A, B, and D. Vertex B is connected to A, C, and D. And vertex D is connected to C, B, and A. So this is an example of a complete graph. Every vertex is connected to every other vertex. The next part is that we have a weighted graph. A graph is weighted if it has a cost or a value associated with traveling it. So I'm going to use numbers on my edges to represent the weight of the graph. So here, from A to B, that cost us 12 units to travel from A to B. Now that might be miles, it might be hours, it might be dollars, it might be whatever unit of measurement that we're talking about. But the weight of edge AB is 12 in this case. Now the total weight is going to be the sum of all the edge weights in a Hamilton circuit. We need to add everything together. So if we continue my path that I started here, going A to B to C to D back to A, first off, I've created a Hamilton circuit because we have crossed every single vertex exactly once and we've returned back to the beginning. But we notice that A to B, we spent a weight of 12. From B to C, we spent a weight of 3. From C to D, we used a weight of 2. And from D to A, we used a weight of 8. So that gives us a total of 25. The total weight, therefore, of that Hamilton circuit is 25. Traveling salesman problem now is concerned with how do we find the shortest or the least possible weight for a Hamilton circuit. Now there is no solution to this. We have algorithms or processes to solve these, but this is an open problem in mathematics and computer science. How do we do this? So the traveling salesman is the challenge of finding a Hamilton circuit on a complete weighted graph for which the total weight is as small as possible. We take 3 possible Hamilton circuits for this graph that we're looking at. Now I've given us the 3 possible outcomes for the different Hamilton circuits that we have. I'm going to go through and highlight those to start off. For the first graph, we go A to B to C to D back to A. And we know that that has a weight of 25. The second option, we can go A to C to B to D back to A. And if we add those, we have 5 and 3 is 8, 8 and 7 is 15, 15 and 8 is 23. That's got a lesser weight. And the last possible outcome, if we go A to C to D to B to A, we have a total weight of A to C is 5, plus 2 from C to D is 7, plus 7 from B to D is 14, plus 12 gets us 26. So for this given graph with 4 vertices, there are 3 different possible outcomes for a Hamilton circuit, and we've identified the least. So that is our solution to the traveling salesman. Now notice geometrically, if I look at this, I can see that I have 3 different circuits based upon the images that I show. And I'm going to highlight these so that I can identify where I've traveled and then add together the different pieces. We're going to have 2 different algorithms to solving the traveling salesman problem. The first of which we're going to call the nearest neighbor algorithm. And we're going to use this, I'm going to say approximate a solution starting at vertex C. Now the nearest neighbor algorithm might make sense, might be intuitive. We're going to start at a given vertex, in this case C. From that location, we're going to find the shortest available edge. So if I look at vertex C, I can travel 5, 10, 6, or 4. 4 is the smallest available edge. So I'm going to travel C to E. I'm going to make note of that, going C to E. I'm going to build my circuit as I go along. Now that we're located at vertex C, I can travel the next shortest edge. Now I'm going to follow the second bullet that I have. From the current location, travel the shortest available edge. I cannot travel back to C because we've already left that, and we've already used that edge. That would be done. We could travel 8, 8, or 9. Well, we've got 2 8s there. Those are both shorter. So actually, we get to choose. I'm going to pick that 8 going up to A. You might pick the other one, and that's okay. I'm now located at A. From the current location, I'm going to travel the shortest available edge. I can travel 5, 8, well, 8's out because we just used that, 11, or 20. Now you say 5's the shortest, but let's look at what happens. If we use that 5, that's not available because now we just created a circuit without getting to our other locations. So 5 is, unfortunately, out. That is not an available edge. Instead, we could travel 11, or we could travel 20. No, that 11 is going to be our shortest, so let's highlight that. So far, we've gone C to E to A to D. Looking at our next available shortest edge, well, from D, 9 would give us 3 lines in, creating a sub-circuit. That's out. 6 closes our circuit. That's out. The only thing, happens to be 2 is the shortest. So let's go D to B, that distance of 2. And now 20 to A, well, that would give us a circuit. Not possible. 10 to C, that's going to give us a circuit, but it includes everything. 8 is out. And so all we're left with is 10. So I have to use that 10. I've gone back to C. And if I add together my weights, we have 4 plus 8 plus 11 plus 2 plus 10. Notice that I'm following my track going around. That gets us a total of 4 and 8 is 12, 11 is 23, plus 2 is 25, plus 10 gets us 35. We might be able to get something shorter, but this is following the nearest neighbor algorithm. We are just following the steps. If we start at a different vertex, we might actually end up with something completely different. So let's see what happens if we say, start at A. If we're to start at A, well, our first vertex is going to be that 5. And now we're at C. We're going to go to C to E next. From here, well, that 8 is no longer available. So from here, we actually could use the other 8. Then I would travel to 2 and the 11. We end up with a different circuit. So the nearest neighbor, the key here is from your current location, we're going to travel the shortest available edge. Now let's take a look at our second algorithm. The second one is called the greedy algorithm. And the idea, rather than our current location, we're going to look anywhere on the graph. So let's see what happens. I'm going to look anywhere on the graph. We've got 20, 5, 10, 8, 11, 2, 8, 6, 4, 9. I just said everything there. The shortest number there is that 2. So we're going to build our circuit. We're going to start at the end, but we're going to build our circuit in pieces. So we're going to use that VD because that is the shortest available edge anywhere. After the 2, the next shortest least valued number is 4. So we're going to use that 4. Okay. Well, here I can see that those two edges are not yet connected, but don't worry, they will be connected eventually. So we're going B to D, C to E, and I can start to build this up. I'm going C to E, and I've got B to D. So I'm just going to put those connections, those links down, and then I can move them around. After that, our next smallest available edge, well, we've got 5, we've got 6. The 5 is the smallest available edge, so I'm going to use that. Now, that's a link onto the CE. So I'm going to put that at the end there, ACE. Notice I don't actually care that I'm starting at vertex C. I'm going to start at the end. So I'm going to find together the pieces, the shortest available edge, the next shortest edge, the next shortest edge, so on. After this, after the 5, we got 20, 10, 11, 8, 8, 6, 9. So the 6 is the smallest. Ooh, but if you take a look at this, that gives us 3 lines into C. That is not going to be a Hamilton circuit. We are allowed to have 1 line out, 1 line in. So we can only hit a vertex with 2 lines, 2 edges. So that 6 is right out. Let's get rid of that. After the 6, one of the 8s must be the shortest edge. Now that 8 gives us a circuit there, which is not allowed. So we actually have to use the other 8. That's the next shortest available edge. That's going to go now. We're connecting B to E. Oh, do that right. So connecting B to E. I can actually maybe just use the power of the iPad to move that closer. This time, the next shortest available edge, well, 20 is out. 11, oh, there's a 10. Oh, 10 is out. And 9 is out. Think about why based upon those vertices. So the next shortest available edge is that 11. So we've gone D back to A. And so there's that link, D back to A. We've got every letter used exactly once. We've added them together. And if I add those, we end up with 23. Is that right? I think I lied again. And if we add those, we have, now, starting at C, we've gone 4, plus 8, plus 2, plus 11, plus 5. We have 4 and 8 is 12, and 2 is 14, and 11 is 25, and 5 gets us 30. Now, sometimes the greedy algorithm is better. Sometimes the nearest neighbor algorithm is better. But we don't actually have a set solution unless we check every possible arrangement. Now, things to remember, those available edges. Available edge is one that does not add a 3rd line into a vertex and does not create a sub-circuit. So if we have something that looks like 3 lines going to a point, that's not allowed. If we have something that closes a circuit within the graph but does not include those extra points, that is not an available edge. All right, try it out. I'll catch you later. Bye-bye.